Hi students, welcome to the session. I am Dr. K. Varada Rajkumar, Associate Professor, Department of CSE, AIML, MLR Institute of Technology, Hyderabad. In our previous class, we learned about AVL tree. In this session, we learn about B tree introduction and B tree of order M and definition of height of a B tree. So, overview of the session. In this session, first we see definition of B tree and why B tree, what is the purpose of B tree, and we see the definition of B tree order of M, and finally we see height of B tree. Outcome of this lecture, at the end of this lecture you all are understand properties of B tree data structure. So, definition of B tree. So, B tree is a self balancing tree data structure that maintains sorted data and allows for efficient operations such as searching, insertion and deletion. It consists of a root node, internal nodes and leaf nodes. Each node can contain multiple keys and pointers to child node. So, this is the important point in B tree. So, up to now we learned about the binary search tree and AVL tree. In those two trees, the node can contain only one key, but in B tree each node can contain multiple keys and pointers to child nodes. In B tree, which a node can have more than one key and more than two children. All leaf nodes are in the same level. So, why we need B tree? So, already we have binary search trees, already we have AVL trees, then why we need B tree? What is the purpose of using B tree? So, in case of external storage, there is a need for faster access. B tree data structures, we use it to organize the data in external storage. There is a need for faster access. So, how we discuss with one example. So, consider this binary tree. I am taking 100 as a root. So, 200, so 300, 150, 50, 70, 60, so 400, 250. So, now I want to access this 400. How many comparisons I am going to do? Here 1, 2, 3, 4. Okay. So, now in B tree we can store more than one key value in a node. So, for example, if I store like this 1, 2, 3, so 100, 200, 300, 400. Now, when I load this node from external storage to primary memory, then in first comparison only we find the 400. That means here in binary search tree, so first we load 100 into primary memory, then it is not matched, then we traverse to right side and again store the 200 into primary memory from secondary memory. But coming to in B tree we can store more than one key in a node, the entire node will copied into primary memory. So, that is the advantage of B tree. So, due to the self balancing nature of B tree, it had fewer levels and thus the access time cut shorts to huge extent by a tree, by a B tree. A B tree facilitates ordered sequential access and simplifies insertion and deletion of records when there are millions of records. If we are maintaining a limited data, then we go with binary search tree or AVL tree. If there are huge data to handle, then we use B tree. So, this is possible due to the reduced height and balanced nature of B tree. If we reduce the height and balancing nature of B tree, then the insertion or deletion and access time will be reduced. So now we see the B tree properties. All the nodes of the tree structure can contain m keys. So it may have m plus 1 children. So what it is? So for example, so this is the node can hold two values. So two values, for example, this is the 50, so this is the 100. Okay, now so this node have m children, 1, 2, 3. Here m equals to 2. So the number of children are m plus 1. Okay, so m equals to 2. So all the less than values of less than 50 we store in this node. All the values between 50 and 100, all the values in between 50 and 100 we store in this node. If the values are greater than 100, then we store those values in third node. Okay, so now all the nodes of the tree structure can contain m keys. So this is the m means number of keys in a node. So it may have m plus 1 children. If here m equals to 2, so the children are 3. M plus 1 equals to, that means 2 plus 1 equals to 3. So every node is at least half full. So contain at least m by 2 items. Here for example m equals to 10. So now so each node at least half full. Half means 10 by 2, 5. If the node have only 4 keys, then we are going to merge. Okay. If n, so number of items in a node is less than m by 2. Here in this case it is less than n by 2. Then merge it with another node, and if n greater than m, then split the node. What it is? For example, here m equals to 10. The number of items are 11. Then you are going to split the node. Why? The maximum number is 10 here. All the key values in a node must be in ascending order. So ascending order means so 50, 100. So for example, if the tree can hold 3 values, so let us assume 18, 13, 20. So now if you observe, all the values are in ascending order. So how many children? 4. So why? Here m equals to 3. So the number of children are 4 here. Okay, so all the less than values we store in first node. Here minus 2, 1, less than 8. So it is a first node. So 9, 11, 12. So 9, 11, 12 are the numbers between 8 and 13, and 14, 19 we store so in third node, because these values are in between 13 and 20. So greater than 20 I store in a fourth node. Okay, so all the key values in a node must be in ascending order. If you observe 8, 13, 20 is in ascending order, minus 2, 1, so 9, 11, 12, 14, 19, 32, 45. All leaf nodes are at the same level. So all the leaf nodes must be at same level. So B tree of order m. So B tree of order m. The order of the B tree is a degree that helps you determine the number of children a node can hold in B tree. Okay. So for example, if the order of B tree is 3, the minimum number of children would be 2 and maximum number would be 3. So what it is? If the B tree order is 3, now so this is the order. Now how many values we are going to store? We store 3. Now so these children's, now how many children's? 4 children's. Now so these children's must have either 2 or 3 values. Okay, so 1, for example, here if I store 9, so this is not allowed. Why? So always it must be at least have at least 2. Okay, so why? Here this is the condition, m by 2. So every node is at least half full, so contain at least m by 2 items. If the order of the B tree is 4, the minimum and maximum number of children would be 2 and 4 respectively. So, B tree of order M means the number of children a node can hold in a B tree. So, height of B tree, the height of B tree depends on the number of keys stored in it. So, for example, if we store only one value, the height may be increased. If we store more than one value, for example 2, then height will be reduced. If you store 3 values, yes, again height will be reduced. So, we understand that, so based on the number of keys stored in the node, the height will be reduced. If the height is reduced, then it is very easy to access the elements in the node. So, B trees are balanced trees, which means that all leaf nodes are at the same level and the height of the tree is minimized to achieve efficient operations like search, insertion and deletion. For a B tree order M and containing n keys, the height h of the tree can be expressed in terms of m and n as follows. So, h means height equals to big O of log m by 2 n. So, m by 2 is base. So, this formula indicates that the height of a B tree grows logarithmically with the number of keys n stored in it with respect to the order m. The base of the algorithm is m by 2. So, because the minimum number of keys in a node is typically half of the order, at least we store more than one key, so it is n by 2. So, height equals to big O of log base m by 2 n. So, let us see one example. A B tree of order 4, m equals to 4. If there are 10 lakh keys stored in it, the height of the tree might be on the order of log 2 10 lakhs. So, why it is log 2? It is log m by 2. So, here what is the m? 4 by 2 equals to 2 here, so, which is approximately 20. So, this algorithmic growth in height allows B trees to efficiently manage large data sets with relatively few levels in the tree. So, coming to summary of the session, in this session we will learn about definition of B tree and B tree, order of m and height of B tree. So, what is a B tree? So, B tree is a self-balancing tree data structure that maintains sorted data and allows for efficient operations such as searching, insertion, deletion. In next classes, we are going to discuss about these operations, searching, insertion and deletion in detail. All the nodes of the tree structure can contain m keys, so m plus 1 children. So, every node at least half full, so at least m by 2 items. If n is the number of items, node is less than m by 2, then merge. If n greater than m, then split the node. So, all the key values in a node must be in the ascending order. All leaf nodes are at the same level. The order of B tree is a degree that helps you determine the number of children a node can hold in a B tree. For a B tree of order m and corresponding n keys, the height h of the tree can be expressed in terms of m and n is big O of log n by 2 n. In next class, we discuss how to search an element in B tree. So, thank you.